Hello and welcome, dear students. Welcome to our advanced analysis session on optimization algorithms. Today we will focus on a highly significant class of mathematical programming, quadratic programming. As you can see on the slide, we are dealing with a quadratic objective function composed of a linear term, c prime x, and a quadratic form, 1/2 x prime c x. This formulation serves as the fundamental basis for the Markowitz portfolio optimization model, where our goal is to minimize risk, which is inherently quadratic in nature. Now take a close look at the constraints. We have a combination of inequality constraints, ax less than or equal to b, and equality constraints, ax equals b. The presence of these inequalities makes solving this problem more challenging than simpler optimization tasks, as we do not initially know which boundaries will be active at the final optimal point. A key point emphasized at the bottom of the slide is the assumption that matrix C is positive definite. This assumption is vital because it guarantees that our objective function is strictly convex. Consequently, any local optimum we find is guaranteed to be the global optimum, and our algorithm will follow a guided descent to reach this definitive point. In the upcoming slides, we will explore how the active set strategy allows us to decompose this complex problem into a series of simpler subproblems. In this slide, we introduce a concept that serves as our compass throughout this algorithm, the quasi-stationary point, or QSP. The strategy of this algorithm is essentially a generalization of the simplex method used in linear programming. Specifically, we move sequentially from one QSP to another, progressively decreasing the objective function's value until the optimal solution is reached. But what exactly is the formal definition of a QSP? According to the slide, a point x0 is considered quasi-stationary if it satisfies two simultaneous conditions. First, it must lie within the feasible region. Second, it must be the optimal solution for the restricted subproblem, where we only consider the constraints that are currently active at that point. Mathematically, this is expressed as minimizing the objective function subject to a sub I prime x equals b sub I for all indices in the active set I of x sub 0. Take a look at the diagram on the right. You can see the contour lines and a dashed path passing through several QSPs. This illustration perfectly demonstrates how the algorithm jumps from one point to the next by dynamically updating the active set. There is a crucial implication here. Since the global optimal solution is guaranteed to be a QSP, and because there are only a finite number of such points in any given problem, the algorithm is guaranteed to terminate in a finite number of steps. This ensures both the reliability and efficiency of our search process. In this slide, you can see the roadmap or the operational logic of the algorithm presented as a flowchart. This iterative structure guarantees our path from an initial starting point to the global optimum. The process begins at the start block, where we establish ourselves at an initial feasible point, xj, with a defined set of active constraints, kj. In step 1, our objective is to find the search direction. By solving a linear system, we determine the vector sj, which points exactly toward the minimum of the subproblem that considers only the current equality constraints. In step 2, we must determine how far we can move in this direction. We calculate the maximum possible step size, sigma sub j, to ensure that no new constraints are violated. In step 3, we update our current position using the formula x sub j plus 1 equals x sub j minus sigma sub j s sub j. Now we reach the critical decision point. We ask ourselves, have we reached a quasi-stationary point, QSP? Our criterion here is the step size. If a full step was taken, sigma sub j equals 1, the answer is yes. If the answer is no, it means we hit a barrier or a new constraint along our path. Consequently, we add a constraint to the active set and return to step 1. If the answer is yes, it means we have reached a QSP. Now we must verify the optimality conditions by examining the Lagrange multipliers. If all multipliers are non-negative, greater than or equal to 0, we have reached the final solution and the algorithm stops. Otherwise, we drop the constraint with a negative multiplier to open up more movement space and return to step 1. In this slide, we delve into the engine of the algorithm, the mathematical computations seen in steps 1 and 2 of our flowchart. Our objective here is simple yet vital: to find the most efficient path to the solution. Step 1. Compute search direction, Sj. In the first phase, we must calculate the search direction, represented by the vector Sj. To achieve this, we solve a matrix system known as the KKT system. As shown in the formula, the matrix Hj is constructed by augmenting the Hessian matrix C with the coefficients of the active constraints, Aj. The output of this system provides two critical components: the search direction vector, Sj, which points directly toward the minimum of the objective function, assuming only the currently active constraints are considered. The vector Vj, containing the Lagrange multipliers, which are essential for deciding whether to drop constraints in later stages. Step 2. Compute step size, sigma j. Now that the direction is known, we must determine the step length, sigma sub j. Our goal is to move as far as possible without leaving the feasible region. First, we calculate hat sigma sub j, which represents the distance to the nearest boundary. We examine our path toward the target to identify the first constraint that would block our movement. Ultimately, the final step size is the minimum of this distance and the value 1. A step size of 1 means we reach the subproblem's minimum directly without hitting any new obstacles. In essence, we always choose the shortest of these distances to guarantee the safety of our movement within the feasible region. In this slide, we aim to answer a critical question. After calculating the new point x sub j plus 1 equals x sub j minus sigma sub js sub j, what does the resulting step size, sigma sub j, tell us? We are faced with two distinct scenarios that determine the algorithm's next course of action. Case A, left, a fractional step, sigma j less than 1. Look at the illustration. The dark blue dot represents xj, and the open circle is the subproblem minimum we intended to reach. However, as you can see, a red line labeled New Blocking Constraint has obstructed our path. What it means: we were forced to stop early because our trajectory hit a new boundary that was previously inactive. Our journey to the subproblem's minimum was cut short. Action required: we must add the index of this blocking constraint, for example, index L, to our active set. Next step: with this more restricted set of constraints, we must return to step 1 and recalculate a new search direction from our current position. Case B, right, a full step, sigma j equals 1. In this image, you see the arrow reaching the target directly without hitting any obstacles. What it means: we have successfully traveled the full distance to the unconstrained minimum of the current subproblem. Congratulations, we have arrived at a quasi-stationary point, QSP. Action required: this point is a potential candidate for the final solution. However, our work is not yet finished. We must now verify the KKT conditions, specifically the Lagrange multipliers, at this location. Next step: based on the analysis of these multipliers, we decide whether this QSP is the global optimum or if we can further decrease the objective function by relaxing one of the current active constraints. We have reached one of the most critical stages of the algorithm. Suppose we have taken a full step, sigma j equals 1, and are now positioned at a quasi-stationary point, xj plus 1. At this stage, we must perform the critical check to determine if we have reached the peak of optimality. To do this, we inspect the vector of Lagrange multipliers, uj plus 1, associated with the active inequality constraints. We look for the smallest value among these multipliers, which we denote as uj plus 1, k. Two scenarios can occur here. Condition 1. All multipliers are non-negative, greater than or equal to 0. Interpretation. If our smallest multiplier is greater than or equal to 0, it means the full Karush-Kuhn-Tucker KKT conditions are met. Geometric insight. Geometrically, no active constraint is pulling the solution in a better direction. In fact, relaxing any of these constraints will not improve the objective function and might even make it worse. Action. The algorithm successfully terminates here. We have found the global optimal solution. Condition 2. A negative multiplier exists, less than 0. Interpretation. If the smallest multiplier is negative, it serves as a vital signal for us. A negative multiplier on constraint k indicates that this specific constraint is preventing the objective function from decreasing further. Our action. We remove this constraint from the active set, kj, a step known as a drop. Result. By removing this barrier, the search space expands. We now return to the beginning of the cycle to find a new search direction within this broader feasible region. In essence, Lagrange multipliers tell us which boundaries are beneficial and which ones are obstructing our progress. Now it is time to observe the theoretical concepts within a practical example. As we mentioned in previous sessions, in the opening slides, every quadratic programming problem is built upon several core pillars, which you can see here. In this model, we encounter matrix C, the Hessian matrix of our objective function. It plays a decisive role in the curvature of the function. Here, this matrix satisfies the positive definite condition, which guarantees the existence of a unique optimal point. We also have vector C, which forms the coefficients of the linear portion of our objective function. Our next parameter is matrix A, which contains the coefficients for the problem's constraints and defines the boundaries of our movement. On the right, you can observe the geometry of this specific problem. We are facing 4 inequality constraints that enclose our feasible region. Each of the 4 lines you see in the image represents the boundary of one of our constraints, which does not allow us to move outside this area. Our starting point, labeled as the initial point in the illustration, is located at one of the corners of this space. As is evident, this point lies exactly at the intersection of 2 of our constraints, meaning that at the start of the process, these 2 constraints are in the active state. In the first iteration, we will see how the algorithm evaluates the status of this point relative to the entire feasible space. In this slide, we enter the operational phase of the algorithm to observe what happens during the first 2 iterations. Iteration 0, a decisive start. We begin at the initial point identified in the previous slide. At this location, our active set consists of 2 perpendicular constraints. By solving the system of equations to find the search direction, we find that our direction vector is 0. As we learned earlier, a 0 direction indicates that we are currently at a quasi-stationary point, QSP. But is this the global optimum? To answer this, we examine the Lagrange multipliers. The calculations show that both multipliers associated with our active constraints are negative. Decision. According to the rule, we identify the smallest multiplier, the most negative value. Action. This negative multiplier signals that one of these boundaries, in this case constraint 3, is severely obstructing the decrease of the objective function. Therefore, we remove it from the active set. We are no longer chained to that corner and are ready to move. Iteration 1. Movement toward a new boundary. In iteration 1, while we are still physically at the same starting point, the removal of one constraint has opened up a space for movement. By resolving the system, a new search direction is obtained, which, as shown in the diagram, points to the right. Now it is time to calculate the step size. We aim to move toward the minimum, but along our path, we hit the boundary of constraint 1. The calculations show that we can only take a fractional step, less than 1, before reaching this new boundary. Update. Our new point is now located at the far right corner. Because our step was not a full step and we hit an obstacle, we add the new constraint, index 1, to the active set. Our active set now contains 2 constraints again, and we are ready for the next iteration. Continuing with our example, we reach the second iteration, where we are now positioned at a new corner of the feasible space. Iteration 2, reevaluating at a new corner. We are now located at the intersection of boundaries 1 and 4. By solving the KKT system for this new configuration, our search direction once again results in 0, indicating that we are at another quasi-stationary point. Lagrange multiplier analysis. Looking at the results, we find that both of our Lagrange multipliers remain negative. Decision and action. Since both values are negative, we must relax one of the constraints. Here we decide to drop constraint 4 from the active set. While our physical location remains the same, this action opens the path for movement in the next iteration. Iteration 3, the final move. In the third iteration, we have only one active constraint, which is number 1. By solving the system again, a new search direction is obtained that points directly downward. Step size. By calculating the distance to the first obstacle, we find that the objective function's minimum is reachable before hitting any new boundaries. Therefore, we take a full step of 1. Result. By taking this step, we arrive at a new point, indicated in the illustration by the downward motion vector. Because a full step was taken, we have reached a new QSP, whose global optimality we will confirm in the final slide. In this slide, we observe the result of all iterations and the algorithm's efforts. We are now in the final state. Our final point, marked with a bright green star in the illustration, has the vector coordinates 4, 2. At these coordinates, only constraint number 1, which is x1 less than or equal to 4, remains in the active state. Final optimality check. As you can see in the calculations, the last move made was a full step, sigma equals 1. This means we have successfully arrived at a quasi-stationary point. However, to ensure that this point is indeed the global optimum, we calculated the Lagrange multiplier for the only active constraint. The value of this multiplier is 2. Since 2 is greater than 0, u1 equals 2 greater than or equal to 0. All KKT conditions for optimality are satisfied at this point. Final conclusion. The algorithm terminates here because there is no other feasible direction to further improve the objective function. Final optimal solution, x star. The point is 4, 2. Minimum objective value. By substituting this point into the function, we have reached the final value of -28. This example clearly demonstrated how the algorithm intelligently uses Lagrange multiplier signals to find its path through the constraints and reach the most accurate possible answer in finite time. In this slide, we will observe all the steps we calculated numerically on the problem's geometric map to gain a deep visual understanding of the algorithm's performance. As you can see in the diagram, our journey began at the top left corner at point x0. At this location, as we previously analyzed, the vector of Lagrange multipliers indicated that staying at this intersection was not beneficial. In fact, a negative multiplier associated with one of the constraints acted as a guide, pointing us toward a profitable path along the boundary of the other constraint. The algorithm then moved to the right until it reached point x2. This point represents our second quasi-stationary point, QSP. Here, our computational system again identified that there was still room for improvement. Once more, Another negative Lagrange multiplier signaled that by dropping the upper constraint, we could further decrease the objective function. Finally, by moving along the vertical boundary, the path concluded at point x4. This point is our final station, the global optimum. The difference between this point and the previous ones is that here, for the first time, all KKT conditions are satisfied, and there are no negative multipliers to lead us elsewhere. This visualization beautifully demonstrates how the algorithm, instead of searching blindly through the entire space, intelligently traverses the edges and corners of the feasible region to extract the most accurate solution in the shortest time possible. At the conclusion of our discussion, it is time to examine the theoretical and powerful features of this algorithm. For a quadratic programming problem with a positive definite matrix C, this active set algorithm guarantees termination at the unique global optimal solution within a finite number of steps. But why can we be so certain? There are three primary reasons, as shown on the slide: strict convexity. The positive definite nature of matrix C ensures that our objective function is strictly convex. In mathematical terms, this means our function resembles a deep valley with only one floor or minimum. Therefore, we never get trapped in false local optima. Finite search space. The number of ways to choose a subset of constraints to be active is limited. Since every station we reach is a quasi-stationary point and the number of such points is finite, the algorithm cannot continue indefinitely. No cycling. The algorithm's strict rules for managing the active set, combined with the fact that the objective function value decreases at every step, prevent the process from cycling indefinitely through the same set of points. In summary, this algorithm performs a methodical descent until the true minimum is found, using the KKT conditions as a guide to intelligently navigate the vertices and edges of the feasible region. I hope this session has provided you with a deep insight into the power of active set algorithms for solving complex optimization problems. Best of luck with your studies.